Yeah, my name is Davi Lazzarotto. I'm going to be talking about this JPEG exploration for standardization of Radiance field technologies. So, well, we've been talking a lot about this today, right? NeRF and Gaussian splatting are all like these amazing technologies that allow to achieve very high quality novel view synthesis, and that's why we've been so interested on this kind of technology. But there are also many challenges related to that. So one of these challenges that's especially related to standardization, so coding standards, it's actually the great number of research works that we have been seeing, right? So this is a chart. It's already a bit outdated. This is from June of last year, but we see the number of papers on Gaussian splatting since well, the inception of this method, right? So we've seen that the number of papers like skyrocketed over just a few months on this number of papers in arXiv, each column here, and well, it is very good for research, right? But in the size where if we want to think about applications and interoperability between different devices, well, each of these methods may employ like a different representation for the radiance field, and so. This kind of variety of solutions poses a challenge for the interoperability, but it's also an opportunity for JPEG and MPEG, so different standardization committees that can step in and propose coding standards for this kind of modality, right? So, well, one of the discussions that we have been having in JPEG is, well, like how do you define this pipeline, like a general pipeline for any radiance field technology where you can get from these like input ground truth images that we see here on the left to a model where you can have like a synthesized novel views like you see here on the right, right, from angles that haven't been seen in the training set. What is like kind of general pipeline? So for that, we took a dive on the in the state of the art and tried to define that. So that's a little bit of what I'm going to do here today, also with you. So, well, first, of course, we have NeRF, right? It was proposed in 2020. And basically the idea, right, is that you want to generate an image given like when you have a model, already trained model, you want to generate an image from a camera in a simulated position, right? So the way that you do it will already mean, no, of course, we cast a ray from each pixel, and then we sample this ray at different points. And you have like a one neural network where you receive as input the direction of the ray and also the position of the points. And for each point, it will generate one value for the density and one value for the color of that position. And then you take all these values and through volume rendering, you produce a color value corresponding to that ray, right? And each ray corresponds to a pixel in the image, and then you have a whole image if you do it for all the rays, right? So, well, for coding, why does it interest to us? Because it is interesting to us to see that because the whole scene is represented by these neural networks, right? Well, actually, there are two in case of NeRF because it's a two-stage sampling process. So the whole information is in two neural networks that then must be coded if you want to send it to someone, right? So the whole information, the model parameters are only the weights of the networks. And you can use any kind of method for a neural network formation to compress that. Yes. So, but then if you go on to the state of the art, you see that there's other methods like instant NGP that use kind of different approach, right? So instead of sampling the neural network, sampling the points and sending them to the neural network first, well, before we establish like these grids on the space, and not only one grid, but multiple grids, right? Multi-resolution grids. And for each grids, well, when you sample the ray, now let's say we have one first point here. We want to establish what are the closest points to this point or in each grid, right? So for instance, you have here this orange and this blue grid, you have only two, but in reality you have more. That you establish what are these closest points. For here, these closest points in the orange grid, and then for the blue grid, you have another set of points, right? And then you do that for all of the points that you're going to be sampling on the rate. So in each grid, you define what are the closest neighbors here. And then after all, when you have this sampling process where you have all these relationships, right? And then for each point, like say here this first point x0, right? You will see the establish like the four nearest this four neighbors on the grid. This is actually a 2D representation. In reality, it will be 8 because it's 3D. And you have one hash table for each resolution, and then you hash the coordinate and you get, well, what's the entry, and then you have a feature vector there, right? So for this first, this orange grid, well, we have, you'll find the feature vectors related to the neighbors, and then you do this linear interpolation to get one feature vector that is related to the x0 point, right? And then you do that for all of the resolutions that you have, and you have like one multi-resolution feature vector. And this is the feature vector that it's inputs to the neural network that gives you then, you know, this density and color value. Like this is a simplification. There are other things, but this is the main spirit behind this technique, right? So now the scene is not represented only by neural network, but also by this multi-resolution hash table. So in the perspective of coding, what interests you is like, you know, if you were to encode to use such a method, you need to encode both the weights of the network and the feature vectors, right? So these are not, to see that this method, if you want an encoding method for this, well, should likely be different from the one from the nerf. And that's why I start to see, you know, this problem with interoperability. Now, nowadays, we also have, you know, Gaussian splatting that we're talking about a lot too. And then Gaussian splatting, the representation is totally different, right? You have a scene space, and what you have there, you have a set of Gaussians, and then you go to your array and you find intersecting Gaussians, and you do this kind of alpha blending to get the color of that pixel. Now, in this case, the scene is represented by the set of Gaussian splats, and for each splat, we have different attributes. Position, scale, rotation, opacity, and spherical harmonics. And then, you know, if you want to encode that, well, you can have to encode the attributes of each splat, and similar to a point cloud with different kinds of attributes that are point clouds. But well, if you want to encode that, you need, you know, different method is probably very highly different from what you use for nerf, right? And then even Gaussian splatting, you have like different types of representation. So even this scaffold JS that we talked about earlier, right? You have this scene space, and then you have you know, anchor points that are established in this space. And then for each anchor point, you have a feature vector. And then this feature vector, and also you have some offsets that are learned during the training of the model, right? And you predict this splat attributes on the fly when you were rendering, right? And then you do the same thing as before. You find intersecting Gaussians. So now in this case, the information of the scene, it's in these anchor points and not in the splats anymore, because the splats are generated on the fly. And each anchor, well, if you were to encode this, you want to encode, you know, the attributes of each anchor and the weights of the neural network that predict the generated splat, right? So again, from the perspective of coding, it's still a different thing. And this is kind of the encoding methods like this will probably differ from if we use the coding method for the original 3GS. And one of the examples here is Context.js. There was also Professor Park that talked about it. There are others too that based on this scaffold.js. So, you know, so yeah, this diving on the state of the art was just to show, you know, that we have different methods for view synthesis for each method. And then when you have different methods for view synthesis, you also have different ways to represent the model. You probably need a different way to code. So so with that in mind, you know, take away that we in JPEG we came up with this processing pipeline for Radiance fields. It's very high level, but it's to find something that is common to all these types of Radiance field methods, right? So you have a set of input images. You estimate their camera poses, and then, you know, we have this model instantiation phase. There is when you train the model, right, and generates a set of parameters. And in the scenario that we're interested in, well, we want to encode that into a bit stream, and then on the receiver side, you decode the bit stream to regenerate the parameters back, and while we do view synthesis to obtain the synthesized image, right? And so we also defined the first version of this scope of JPEG RF, so Radiance fields, and the scope being the creation of a coding standard for Radiance fields, offering a compact representation for models, enabling the immersive depiction of 3D scenes given a set of input images from different viewpoints, right? So if you take a look at the the block diagram that I had before is really this part of encoding and decoding. This is the part that JPEG is really interested to take a look. But one thing that is important to realize when you see this pipeline is that an encoding mechanism that you define here actually depends a lot on the method that you use for model instantiation, as we've seen before, right? But in the other hand, the model instantiation process can also be optimized based on the coding mechanisms that you use, because since everything is learned, you can learn the parameters in model instantiation in such a way that they are good for encoding with specific methods, right? So we have this interdependency of all the blocks in the mod of the pipeline that happens, and see that we cannot take a look at each one of them just in an isolated manner. So these help us guide us on activities have been guiding our discussions in JPEG since we even if we define that our standardization target is the decoding process and the syntax for the bit stream. Actually, we also need to take a look at this model instantiation and view synthesis very carefully, and that's why we're exploring the JPEG committee is exploring how to work with different model instantiation and view synthesis methods, and then how to compare these methods, their overall performance, considering this entire pipeline, and not only focusing on one method for now. And so, just already concluding for what it means for JPEG, is that on one hand, we see this need for coding standards because of this wide variety of representation formats for radiance fields. And the JPEG committee is really well placed to address this issue. And since, these elements of the processing pipeline that we identified, they are really interdependently and rapidly evolving. Well, even if our scope is the creation of the coding standard, we are also want to remain open to accommodate different innovative techniques for model instantiation. When I mean instantiation, also can be translated as training, right? And for the view synthesis. And we see as in a way that decisions regarding these elements, even if they are not standardized, they can be crucial for the success of a coding standard. So to conclude this, our group now we have is going on when we have different mandates, which include first, we're working in a state of the arts and challenges document, where try to map what are the field right now, and also the challenges related, also including the use cases and the requirements of these technologies. So this is something that's also very important for us to define. We're also working in the common test conditions. So basically, what are the conditions that should be used in JPEG to evaluate different coding proposals? And also, we've been conducting exploration studies, to have a more practical experience in that too. Now I included here some context from JPEG. So convener, the Turaj Ibrahimi, also the subgroup requirement subgroup chair, so Fernando Pereira, which is the group that is sponsoring JPEG Radiance fields, and then myself and Stuart, which is the co-chair. And anyone that wants to get involved in this standardization activity are welcome to participate in these ad hoc group meetings that we're having that are open. So if you want to participate and you don't know how, where you can just contact us, any of us here on the screen, and we can provide you with information, right? So yeah, on my side, that's it. Thank you very much.